Now, our next momentum concept we're going to consider is the idea of conservation. And if we consider a system and define it just right, the momentum of a system before and after an interaction is the same. And we express this as the law of conservation of momentum. And there's two crucial pieces of the puzzle. One, we have to figure out what the system is, okay? And then two, we have to think about the system before and after, and we ignore the messy details of during. Okay, we don't have to worry about that. That's why this formalism is especially helpful. And at this level, this is not a new law of physics, but it is a different way of looking at the world, and it gives us tools to solve certain kinds of problems that would be extremely difficult to solve using forces and the types of things we've looked at previously. Now here's an example of the type of problem that we're going to be considering. Okay, so Chelsea is moving forward at 1.8 meters per second. She throws a 200-gram softball horizontally at a speed of 23 meters per second. In principle, she'll recoil. She'll be moving forward less quickly after throwing the ball. What is her speed after the throw? And Chelsea here was a softball player with the CSU club team, and she was very, very happy to actually let me take some videos of her throwing a softball, and I had her throw a softball really, really fast while she was up in the air and was able to get some data, so I had kind of a clear situation. Now let's start with our strategy. And for strategy, in problems like this, we need to be considering situations where the forces are large and the time intervals are short. And particularly the time intervals being short is what I'm going to focus on right here. We want to consider a situation where we can treat a system as being isolated. The whole world shrinks down to just a couple of objects, and that's the system. And the momentum of that system is going to be conserved. And so a crucial piece of the puzzle is to say, what is the system? What is the system that is going to be isolated and for which momentum is going to be conserved? And in this case, the system is going to be Chelsea plus the ball. And when she was throwing the ball, the force was so large between her and the ball and she was up in the air and she threw the ball very, very quickly. So a short period of time she's in the air. Basically, we can say we're just going to treat only Chelsea and the ball in isolation from everything else. And so the system is just somebody up in the air throwing a ball, and we draw a border around it. In the textbook we do this and we say that's my system, and the system basically doesn't exchange anything with the environment. It's just Chelsea and the ball. We focus all of our attention on that. Now, given that we've decided we can do that, our next step is to prepare. And the preparation step is always, we're going to draw a before and an after picture. And it's really important that you do this in order to be able to keep things straight, particularly in problems like this. If you don't draw the picture, you are going to run into trouble. And let's go ahead and take a look at this. And here's what the situation looks like. So before, I've got Chelsea, and Chelsea is holding a ball, and both of them together are moving forward at 1.8 meters per second. Okay, and after she throws the ball, here's what happens. Here's Chelsea, and here's the ball. The ball is moving at 23 meters per second, and that was with respect to the ground. And Chelsea is moving at some final speed, I'm just going to call it VC, the speed of Chelsea. Okay? Now, we can compute the momentum before and the momentum after. And the momentum before is this. So initial momentum is just going to be equal to the mass of Chelsea plus the mass of the ball, because both of them were together, times 1.8 meters per second. The momentum after, if we look at that, is going to be composed of two parts. It's the mass of Chelsea times the speed that Chelsea is moving at, plus the mass of the ball times the speed the ball is moving at, which is 23 meters per second. Okay, so that's the situation that we have. We've got an initial momentum, we have a final momentum, and we've decided that we can treat this as a conservation of a momentum problem, and we can set these two equal to each other. And with that, we are ready to do some solving. And to solve, I'm just going to say, let's just set my initial momentum equal to my final momentum, and that my initial momentum was the mass of Chelsea plus the mass of the ball times 1.8 meters per second, which was the speed that she and the ball were moving at, is equal to the mass of Chelsea times her final speed plus the mass of the ball times its final speed, which is 23 meters per second. Now notice in the problem statement, I'm given the mass of Chelsea, I'm given the mass of the ball, and so I know the mass of Chelsea, I know the mass of the ball, I know the final speed of the ball. The only thing I don't know in this equation is the speed of Chelsea, and I can solve for that. And if I do that and I round it off to two significant figures, as we do, we come up with the final speed of Chelsea of 1.7 meters per second. Final piece of the puzzle, of course, is to assess. We get a speed of 1.7 meters per second. Does that make sense? Well, I actually took video of this and I did video analysis, and in fact she did slow down to 1.7 meters per second after the toss. And so it works out. I mean, the data matches what the physics calculates as better be true, otherwise I am living a lie, and that is something I refuse to do. And now notice the simplification that we've made. She's wheeling the ball around in a circle, okay? She's doing some circular motion with the ball. The force she's applying to it certainly varies. We don't care about any of that. The only thing we care about is the before and the after, and the messy details of the actual throw we're insulated from that. And so it's a great simplification for solving certain kinds of problems. And let's look at one more example. And this is one of a peregrine falcon. And peregrine falcons hunt by basically slamming into things. They're on the wing, they get going very, very fast, and they slam into things. They do other stuff as well, but this is one way that they hunt. And this is actually data that I got from the folks at the Raptor Center. And they gave me typical numbers for falcons and pigeons. And I kind of took an extreme case, but I have a 450 gram peregrine falcon moving at 80 meters per second, slams into a stationary 250 gram pigeon. Now the pigeon's probably moving, but it's not moving at 80 meters per second, so we can ignore that. And the collision is quick, taking only about 0.01 seconds. Question, what is the net force on the pigeon? Okay, that's our question. Now our first piece of the puzzle is to... And in strategizing, we're going to say this. Okay, look, the collision time is 0.01 seconds. That's really, really short. And so as a consequence, the force is going to be large. And so we are entitled to treat this problem as a conservation of momentum. Okay, so we can treat this using the ideas of conservation of momentum because I've got a short time and I have large forces. And so we're going to ignore the details of the interaction and just consider this as a conservation of momentum problem. And the whole world kind of like shrinks down to just the two objects that we're considering, which is the falcon. So here's my falcon. And it's flying downward and it's hitting a pigeon. The falcon's moving at some speed. Pigeon, we said, was stationary. This is our system. The only thing we have to consider is the falcon and the pigeon, and anything else that is acting on them. Drag forces, lift forces, weight forces are negligible in comparison to the force between them. So having simplified the world in that way, we can solve for the force on the pigeon. Now, let's take a look at the next piece, which is our preparation. And in our preparation, as always, we draw a before and an after picture. Okay, we draw a before and an after picture. Okay? And the before picture looks like this. I've got a falcon moving at a speed of 80 meters per second. And I have a pigeon, which is stationary. That's my before. And then after, I've got this. I've got a falcon and a pigeon moving together at a common final speed, VF. Okay? And so, the situation before the collision was the initial momentum was just equal to the falcon's momentum. It's just the mass of the falcon times the speed of the falcon. Okay? Oh, and we know what that is. That's 80 meters per second. My after case was I have the Falcon and the pigeon is the total mass in motion, and they're moving at a speed of VF, which I don't know what that speed is. And actually, it's a prerequisite for solving the problem that we're going to have to do that. And so our next step is going to be to figure this out. And then we'll have one more step that we can do using the same before and after picture, because ultimately we're concerned with forces. So if we find what VF is, we'll double back and do the force later, but let's start with that. So our solution looks like this. We're going to equate the two momentums. We'll say the initial momentum is equal to the final momentum. And so the initial momentum is the mass of the Falcon times 80 meters per second is equal to the mass of the Falcon plus the mass of the pigeon moving at a speed VF. Okay? That's what we're going to get. Now we know the mass of the Falcon, we know the mass of the pigeon, so we know these numbers. We know this number. The only thing we don't know is this number. So with everything in hand, we can solve for what the velocity of the two of them are after the collision. And we get a final speed of 51 meters per second. That's what we get for our final speed. But that's not what we're looking for. What we're looking for is the force on the pigeon. And here's the thing, remember, we're treating this as a conservation of momentum thing. So now we're going to come back to the impulse idea that we saw in the last slides. And the pigeon wasn't moving, and then the pigeon was moving at a speed of 51 meters per second. So now focusing on just the pigeon, but not the whole system, my before and my after picture looks like this. The pigeon's initial momentum was equal to 0. The pigeon's final momentum is equal to its mass, which is 250 grams, times its, and actually let's put that in kilograms, so 0.25 kilograms, 0.25 kilograms, times its speed, which is 51 meters per second. Okay, that's my initial and my final momenta. And so the change in momentum, delta P, is just equal to the final momentum. So 0.25 kilograms times 51 meters per second. And we can use that to figure out the forces. So after doing our conservation of momentum thing, we double back and we say next piece of the puzzle is to look at impulse. We know the change in momentum. And remember, when we did impulse problems, we said that the average force was equal to the change in momentum divided by the time interval. Well, we know the change in momentum, and we also know the time interval. It's only 0.01 seconds. So with that in hand, we can calculate a final value of the force. And if I do that, I get a final value of about 1,270 newtons. Now let's just double back and do some quick assessment. And I want to look at a couple different pieces of the puzzle. First off, when we said we're going to treat a problem like this using momentum, we said that the force was large. So we took the Falcon and the pigeon and we considered them as a system. We'll look at the forces between them, 1,270 newtons. Well, the weight of the Falcon is only about 4.5 newtons. And so the force is gigantic compared to the weights, and also clearly gigantic compared to any weight force or drag force or anything else. So we're absolutely justified in saying the force is large. We are also justified in saying that the time interval is small. It's 1/100th of a second. So large forces, short time intervals, and so that works out. And we end up getting a really, really large force. And here's the thing. The Falcon is withstanding that force on its talons, which are built to take it. The pigeon is withstanding it on some other part of its body, which is not built to take it. And so we're expecting kind of an untimely end for the pigeon. And in fact, that's exactly what happens. And so our final assessment is this result seems reasonable. Okay, I want to do one more example of this. If you lie on a board that is free to move, and you measure the acceleration of you as you're kind of like lying there, you're lying on a board and it's free to move, and so you're kind of can accelerate along the axis of your body. In fact, initially you'll see that your body accelerates towards your feet and then subsequently accelerates towards your head. And here's the question. This happens when your heart beats, and when your left ventricle contracts, your body moves downward. And then, subsequently, it rebounds and moves upward, and the second peak is actually bigger than the first peak. And I want you to think about what is happening here. And the first question is, of course, to consider what is the system? What is the system in this case? And the system is your body plus the blood in your body. And so it's working like this. Your body plus the blood in your body is sitting there. The blood all of a sudden gets a hankering to move towards your head. And so as a consequence, your body has to recoil and it's going to go towards your feet because the total momentum of you plus the blood in your body is equal to 0. And so since the momentum is conserved, any momentum of your blood moving upward has to be compensated by momentum of your body moving downward. But then what happens is the blood reverses direction. It was moving upward and it turns around and moves downward. And that's a double change. It was positive and then becomes negative. And so your body is subsequently going to recoil and go in the opposite direction. And that has to be a bigger change. And so you will move then towards your head. It's kind of a remarkable thing. And then you get this extra peak as your blood slows down. But you can actually use this technique to measure the ejection fraction, like how much blood is ejected from your heart, because it's easy to measure the speed at which blood is ejected from your heart. It is hard to measure the mass of the blood. And this is the way that you can do it. And it relies on the fact that when the blood is ejected from your heart, it goes to this aortic arch, and most of it turns around and heads towards your feet. This is called the Ballistocardiogram. It's a kind of a fascinating application of these momentum ideas. Now, the next piece of the puzzle, we're going to consider energy. And energy is another conserved quantity, and we are going to use this to solve all kinds of problems. And for that problem, the animal we're going to consider most closely is going to be the kangaroo, and I'm obsessed with them, and why that is and what is special about kangaroos we'll talk about in our next topic.